This is the new Bell Mac 32 microprocessor. It is 1 square centimeter of silicon. A 20-foot by 20-foot drawing of its circuitry reveals its awesome complexity. It has over 150,000 transistors or gates, over 300,000 internal connections, nearly 600 inches of interconnecting wires, all in 1 square centimeter. The Bell Mac 32 microprocessor makes use of a design technique known as domino CMOS to increase its operating speed. In this analogy, falling dominoes represent electrical current passing through electronic gates. Each gate must completely open before the current can pass to the next gate. Using domino CMOS in the Bell Mac 32, the gates are packed together more closely. When a gate begins to open, it starts a chain reaction. The time delay between each gate opening decreases, so in domino CMOS, fewer electrons are required to move through the circuit. This saves energy. Partly because the Bell Mac 32 was such a complex project, planning meetings focused on close coordination and management. Development of the microprocessor involved simultaneous, parallel, and interrelated activities. Circuit design, architectural layout, plans for making and testing the chip, and finally, reviewing the requirements of larger systems within which the microprocessor would operate.
The methodology that we use in this is to decompose a very complex system into many manageable small pieces.
What this allows us to do is to partition the job among a number of people. And each block would be the responsibility of one individual designer working with the logic designer in the architecture logic team.
The entire project, if you will, has not been burdened by the need to put together large boards of integrated circuits to test to see whether the design is going to work. The design has been tested on a computer. The design has been laid out with the aid of computers.
Computer-assisted design starts with logic design. Engineers use simulation programs to test the logic and to determine how fast each logic function will operate. Critical paths in the logic can then be altered to improve chip performance. Layout designers then convert the logic functions into a detailed representational diagram of the chip section. That drawing is then converted into symbolic language, which places all the design information into the computer. The computer produces the finished engineering drawings.
It's the job of the computer then to take those small blocks, which have perhaps 100 transistors or so, stitch them together into super blocks, which would be about 1,000 transistors, then into the larger, if you like, jumbo blocks, which are about 10,000 transistors, and then stitch a number of these together to make the whole chip, which is 150,000 transistors. There are checking algorithms that are used to make sure that the interconnections are correct. You then are completely 100% sure that what the engineer has designed in the stick diagram really corresponds to what the computer architect intended.
Making the silicon chip required state-of-the-art manufacturing techniques developed by Bell Laboratories. New photolithographic methods, new metal silicides, thinner diffusions, and new ion etching, all of which allow more complex circuits on smaller areas of silicon.
Tradition in our end of the business has always been to end up with chips that are much larger than we originally expected, and we have now broken with that fine tradition. There were no surprises. The chip size came in within about 0.5% of its projected value.
When you consider there's 150,000 transistors on that chip, and there was not one problem found in silicon, but they were instead found in the simulations and the test of the software that was used to develop that. And by the way, there were only 10 problems. And we know what they are, and we have workarounds for those. I think that's a fantastic statement to the use and the success of the computers.
This allowed us to bring the job in on a very short schedule, about 1 year, as compared with the 3 years or so that would have taken with the conventional design techniques.
In terms of logic design, the technological advance, if you will, is really getting a 32-bit architecture, a complete, full 32-bit architecture onto a single piece of silicon.
The challenge was accepted by many Bell Laboratories engineers and support personnel. And through the use of advanced design tools, Bell Labs engineers created in 1/3 the normal development time a microprocessor for the information age, the Bell Mac 32. This state-of-the-art device will provide lower-cost, high-performance processors for use throughout the Bell system.